We are Team 11. This is our smart lock.
Alright, so picture this. You're leaving the house, you've got a couple of errands to run, you're a little pressed for time, but you feel like something's missing. You left something and you realize it was your house keys, and now you're locked outside the house. You've got to call someone to get out of the spot. Except with our smart lock automatic detection system, this could be a thing of the past. Raspberry Pi connectivity, wireless integration, and app functionality can get you back inside.
Now I'm going to explain how our Python code detects inputs from the keypad to open our smart lock if the passcode is correct. We divide the keypad into rows and columns. A simple keypad has several switches organized in a grid with one switch per character or number. Rows are set as outputs, meaning the Raspberry Pi 4 sets one row at a time to a higher voltage, 3.3 volts. The columns are set as input and pulled down to ground 0 volts via pull-down resistors. Internal wires connect the individual rows and columns. When a user presses a switch, it connects in a specific row to a column, allowing the high voltage from the active row to reach the corresponding column. This column, normally at 0 volts, will now be at a high voltage level. By knowing which row is currently set to a high and detecting which column reads high, the Raspberry Pi 4 can determine the specific key that is pressed.
Here you can see the block diagram for our smart lock. Our smart lock uses a Raspberry Pi connected to a rechargeable battery with an inside button input on the inside of the door and a keypad input on the outside of the door. The Raspberry Pi can communicate with Bluetooth devices for our Bluetooth proximity function, and it sends and receives information from our Android application through the use of the Firestore database on Firebase, and the Raspberry Pi uses all that to control our door lock servo. This flowchart gives a basic overview of the Python code on a Raspberry Pi. Once the Raspberry Pi is initialized, it will get all the initial settings from Firebase and then determine the initial lock state. If unlocked, it will see if the automatic relock setting is true, in which case it would lock after the preset amount of time. If not, it will check for the inside button, keypad lock button, or app lock button, which would then lock it instantly. If not, it will stay in the unlock state. In the lock state, Firestore will be updated and checked for any app changes. If the inside button or app lock button are pressed, it will go right to unlock. If a keypad number is pressed, it will then store that entered code, and if it matches the passcode, it will unlock. If not, it will check the temporary passcode, and if that temporary passcode is still active. If the enter button on the keypad is pressed without entering the code, it will try to connect to Bluetooth 1, and then check the RSSI value of that. If not, it will check Bluetooth 2, and then check the RSSI value of that. If the RSSI value shows that it's within range, the door will unlock. Here we can demonstrate for you how our app interfaces with our Cloud Firestore on Firebase. We can send a lock signal to our lock, we can check the status, and then on our settings page you can see the multitude of settings that we have here available to be edited. For instance, our lock code is currently set to 147. We can change that to 8421. Our temporary lock code can be set to 5757 for 5 hours. The Raspberry Pi will add a time on here just in case there's a reset that happens. It'll still be available for 5 hours. And we can also go in here and reboot the Raspberry Pi through the app and change the Bluetooth MAC addresses that work with the proximity.